critical part of gate sizing, right? And the summary of gate sizing is as shown here. Basically, if the number of gates in the path is fixed, that is n is fixed, then the stage delay should be made, or the stage effort should be made equal for all stages. You should not have one gate doing more work than the other gate. Okay, and therefore it has to be the net minimum delay that is achievable in that way is nf power 1 by n plus p, right, where p is the parasitic effort, right, and f is the stage effort, where f is equal to capital G into H, path logical effort into path electrical effort, which is output capacitance by input capacitance, right? Now, on the other hand, if you have very few gates in the path which is driving a very large load, then this minimum delay is not sufficient. You're still going to have a lot of effort being put in by each gate, right? As you saw in the example that we did, we had an stage effort of 10. Now that was too much, and we got a delay of 46. Then we said that the reason for that was f power 1 by n is not being made small enough. Ultimately, that's where you're gaining. So if you look at this equation, n f power 1 by n plus p, you have the delay scaling as n, right? If n increases, my delay goes up linearly with n, but the delay falls as f power 1 by n. So these two are fighting each other, right? So you must try to reduce f power 1 by n as much as possible without increasing, until the n starts dominating in the sequence, right? And therefore we said that you can actually insert buffers in the path and still reduce the delay of the path. Okay, this buffer insertion algorithm was discussed, and we said that the optimal stage effort is approximately 3.59. We said making it 4 is not a bad idea, because ultimately in your standard cell library you will have gates which are of 2x, 4x, 8x, 16x and so on. So that's why even this fan out of 4 delay is a very magical number for digital circuits. Okay, and so the optimal number of gates after buffering should be log to base 4 of the path effort f, right? And this we basically solved, and then you can find the optimal delay as nf power 1 by n hat plus p plus n minus n1 into the delay of the inverter. That's missing here, right? So further we said that if you want to reduce the delay of your circuit or of your path any further, the only way is to reduce the logical effort, because the electrical effort H is simply output capacitance by input capacitance. It is fixed. Nothing you can do about it. You're given a load, you're given the first gate's input capacitance. You anyway would not want to upsize that too much. You make it unit gate, right? So you take the ratio, this is fixed. The only way you can reduce the delay any further is to reduce the logical effort of each gate on the path. So in the rest of the module, that is what we are going to look at. We are going to look at methods in which I can reduce the logical effort. Okay. So before I reduce the logical effort, let me also deal with another important concept. Suppose I have a NAND gate here. A, B, and A and B, right? So size is 2, 2, 2 and 2. Okay. Now my question is, logically, these two inputs are identical. I can swap these two and still not change the logic of the circuit, right? I can't do this, of course, with A plus BC. I cannot just swap any of the inputs. Logic will change, right? Now, when the logic is identical, which input should I feed to which transistor? Is there a choice? Are they equivalent or not? And this question also comes in this AB plus BC plus CA circuit that you did, right? You have 3 transistors and you have to pick the transistors and assign the inputs appropriately. Okay. So let's look at this and let's look at the pull down part. B and A. This is 6C. This is, how much is this? Sorry. One second. Right? So we had studied this earlier, the propagation delay and the contamination delay. We said that the propagation delay, PD, was 7 times RC, whereas the contamination delay was 6 RC. And the reason for that is this intermediate capacitance here has already been discharged, right? Therefore, if I now need to only discharge the top capacitor, the 6C capacitor, that's going to be a little faster than discharging both these transistors together. So clearly there is a difference in these two inputs, right? And therefore, when you have a critical input, when I say critical input, I mean a timing critical input, then that input has to be connected to the transistor which is closest to the output. Okay. So for example, these two signals A and B, right? A might actually switch early, but B might switch later. Okay. So when I say A is switching early, it means that A has switched to logic high, already discharged the capacitor, and is now waiting for the input B to switch. When that input comes, you want the delay to actually be minimum. So if I connected this to B and this to A, then what would happen? The top transistor would have switched to logic 1. It would have sort of charged this intermediate capacitance also to VDD minus VT, and it will be waiting. When the new capacitor, when the new input comes and switches, then it still has to discharge both capacitors. Therefore, the signal which arrives last, that is the timing critical signal. Okay. So the rule is signal or the input that arrives last What do I mean by arriving last? It means that this transition happens later, right? Arrives last should be connected to the transistor closest to the output, right? So this statement is true even if I have a NOR gate. If I have a NOR gate with a PMOS stack, then the input that arrives last should be connected to the PMOS transistor which is closest to the output. Clear? So what is an example here? Suppose I have a NAND gate, let's say with a signal like this, reset and an input A. Now this reset is, very not timing critical, right? So therefore you connect that guy to the bottom transistor. The signal A is basically the critical signal which is going to control the stuff inside your circuit, right? So that has to switch as fast as possible, right? It is this signal that is going to make many transitions during the functioning of the circuit. Reset is occasionally it will go low or something like that, where you shut off everything and bring the whole circuit to a reset condition. So that's a less critical signal. Connect that to the transistor, which in this case should be A, right? So I'm going to connect this to A and this to B, or okay. Maybe I will just call this as this to be avoid confusion. I'll call it signal X. Okay, so this is input ordering. Okay. Now I can take this one step further. Input A is very critical. Reset is not a critical signal. It's going to happen very few times. Okay. So now let me see how I can improve the logical effort of this input X. Right? The question I'm going to ask is, should this NAND gate have a sizing of 2222, or can it have something else where I can help the signal X to switch faster? Okay, so let's look at that case now. So we said this was B, A, B. Of course, this, it doesn't matter. Okay, the original sizes that we have are 2, 2, 2, and 2. Now, in order for, okay, let's assume that this NAND gate is sitting in a path somewhere. Okay, I have this A and B signal here driving something else. Okay, I have another inverter here, let's say. Now, if I want the path delay on this path to be minimum, what should I do to the logical effort on this input B? Should it reduce or should it increase? It should decrease, right? Now, in order for logical effort to decrease, should the capacitance on that transistor decrease or increase? It should decrease, right? So think about it. What is logical effort? Logical effort is a measure of the capacitance offered for a given pull down resistance or a pull up resistance on the stack. So the resistance is actually coming from the stack. It's not just from that one transistor, because there is one resistance from here, another resistance from here. These two together give me a resistance R. Okay, and we made this equal to R by 2 and R by 2 in our original sizing, where I could not choose between the two inputs. The two inputs were equivalent, and in most cases that's how it is. A and B are equivalent. Of course, even there with input ordering, I could slightly give preference to one input over the other, but the logical effort of both inputs is still 4 by 3. Doesn't change, right? Now what I'm saying is, I want to reduce the logical effort of this input B further, but I need to ensure that the resistance of the stack doesn't change. So what I'm saying is, this R by 2 and R by 2, I'm going to make it some R1 and R2, such that R1 plus R2 is R. That cannot change. However, I want to reduce the logical effort of the input B. Okay, so logical effort of input B is the capacitor of the NMOS plus capacitor of PMOS by 3C. Right, this is what it is. If you take the sizing of 2, 2, you will get 2C plus 2C by 3C, 4 by 3. Okay. Now the PMOS, there's only one transistor. I can't do anything there. When the input B switches, I need the PMOS to pull up with the resistance R. Therefore, that has to be 2. I cannot alter that. This is fixed. Only thing I can do is now drop the resistance of the NMOS transistor, or drop the capacitance. I'm sorry, drop the capacitance of the NMOS transistor. Okay, so instead of 2, I'm going to make this sizing as, let's say, 4 by 3. Just some number. You can choose other numbers also. 4 by 3. So what is the resistance that is being offered by this transistor now? 3 R by 4. Therefore, what should the resistance of this bottom transistor be? R by 7, which means this 2 now should become 4. So what have we done? We have kept the net pull down resistance the same, but dropped the capacitance that this particular transistor is offering to the previous guy, and thereby reduce the logical effort. Clear? So what is the logical effort of this, of the two inputs now? GA and GB. GA and GB. What is GB first? What's the NMOS capacitance? 4 by 3? 4 by 3 plus 2 divided by 3. Correct? So what do you get here? 10 by 9. What about GA? It is 4 plus 2 divided by 3. How much is that? 2. Okay. What was the original logical effort that we had for these two? I'll put it in bracket. 4 by 3 and 4 by 3. So what has happened? 2 is greater than this, right? However, this is less than this. So this is called an asymmetric gate, because the two inputs are not symmetric any longer. They have different sizes and therefore different logical efforts. Right? So the same example that you take where you have a reset connecting to this, I will not only ensure that the reset is connected to the bottom transistor and the signal is connected to the top transistor, I will make the gate asymmetric, not skew it. I will make the gate asymmetric by sizing it like this. Of course, you can now do various kinds of sizing. This 4 by 3 and 4 is just one example. You can do any n plus 1 by n and n, or n plus 1, and get the same result, right? And in the limit, the logical effort of this critical input will approach what? 1, which is as close as you can get to an inverter. You cannot get better than an inverter in any case. The static CMOS inverter. Actually, you can get better than that. So I take the statement back. We'll come to it later. Clear? Any questions here? Yeah. Yeah. So that is the key point that I'm trying to make here. See, when I say logical effort is a measure of the capacitance that transistor offers, or that input will see for a fixed resistance of the stack. The resistance is not coming only from its transistors or whatever transistors that input is connected to. Resistance is coming from the entire stack, right? Therefore, you have these two resistances here, which are contributing to the total resistance. So what I'm doing is I'm ensuring that the total pull down resistance is the same. you're right that because I've made it 4 by 3, right, and not 2, the resistance of that transistor has gone up. But the resistance of the bottom transistor has come down now. So what is slightly counterintuitive is that the resistance of the guy you're trying to reduce the logical effort for is actually going up. The resistance of that guy is not coming down. It's actually going up because I'm reducing the capacitance, right? So it doesn't matter if the resistance of that guy goes up as long as the stack, another transistor on the stack is able to compensate for it. Yeah. Well, that's not possible, right? That's not possible. Therefore, that's why I said you can make it any n plus 1 by n. So if I make this, just think about this. Theoretically, right, I can make this as n plus 1 by n and this as n plus 1, right? Net resistance if you take, you will get R by n plus 1 into n plus R by n plus 1, which is just R, right? So therefore, this resistance will approach this logical effort. If I take n tends to infinity, will start approaching 1. But you can't do that. Now, of course, practically, when I try to implement a layout of an arbitrary n plus 1 by n, when n is very large, then the layout itself becomes so asymmetric that all the assumptions we made will break. Right? This whole thing of, okay, there is only one, capacitance here. There is no capacitance. We don't double count that capacitance. All that will break because the layout has become so asymmetric. That's why the suggested number is 4 by 3 and 4. That's a practical thing which is going to work even at a layout level. Theoretically, you can do any n plus 1 by n. Okay? So what happens to the parasitic delay? So again, the only thing, yes, so that will change. You got to, recalculate all that a little bit. And in fact, even here, you're right that, you have to look at the layout. You have to look at the layout now. However, it is still true that parasitic delay does not change if I upsize this gate. That still remains true. Therefore, my gate sizing algorithm still doesn't care about it. It's a constant number. You have to calculate a new number. It's a constant number. Forget about it. That's all. You have to do Elmore delay again to get this number right. And in fact, that in between capacitance here, you have to recalculate a little bit. It may not even be true that it's a shared uncontacted diffusion and stuff like that. So you have to, I would just say you have to rely on simulations on the RC extraction netlist. Okay? Okay. So now, so just by the way, this is basically known as an asymmetric gate. Where the inputs are not symmetric any longer. Okay?